Hello dear students, in the previous session we were discussing Riemann integral, right? That is nothing but definition and existence of your Riemann integral. In this session, using that concept, let us solve some problem so that you can understand the concept even more better. Okay. The first problem is, show that f of x is equal to x belongs to Riemann of closed interval 0 comma c. That means you have to prove that this function is a Riemann integrable. If I want to prove this function as a Riemann integrable, in the previous session we have seen that if I want to say any function is Riemann integrable, then its lower sum and upper sum should be equal, right? That means lower Riemann sum and upper Riemann sum should be equal. So now let's solve this problem and let's prove that it is a Riemann integrable function. So first, what is my first step? We have seen that if I consider a general interval, say a to b, it is a closed interval. First I have to make this as a partition, right? That means I have to divide this interval into n times. In this, h is nothing but b minus a. So we have seen that I can divide my interval in this manner, that is n subintervals. So using this formula I can do partition with my interval 0 comma c. So I will denote that partition as b. In this interval, what is the value of h? B is nothing but c and a is nothing but 0. So c minus 0 is c. So the value of h is nothing but c. Right? So now your partition will be, you have to substitute the values in this manner, that is 0, 0 plus c by n, 0 plus 2 c by n, so on up to 0 plus n c by n, that is nothing but your b, right? So now my partition will be 0, 0 plus c by n, 0 plus 2 c by n, so on 0 plus I minus 1 into c by n, comma 0 plus I c by n, so on up to c. This is the last one. So we are dividing our interval into n subintervals, right? So now what is mi? Mi is nothing but, it is a infimum of the function f of x in the subintervals xi minus 1 comma xi, right? So I can define mi as f of xi minus 1. So f of xi minus 1 means we can write this as f of I minus 1 into c by n, right? So this is nothing but I minus 1 into c by n, that is I minus 1th subinterval we are choosing here, which is nothing but your f of xi minus 1. Since the function is x, we will replace x by I minus 1 into c by n. Okay. If you have function f of x as x square, then it will be I minus 1 into c by n the whole square. So now this is my f of xi minus 1, or we can write it as small mi. Similarly, I have to find out capital Mi. Capital Mi is nothing but f of xi. So f of xi will be ic by n. This is your f of xi, right? So now I have to find out the value of delta xi. Delta xi is nothing but xi minus xi minus 1. So xi is ic by n minus xi minus 1 is I minus 1 by n into c. If you solve this, you will be getting c by n, right? So now delta xi value is c by n. Now I have to find out LPF and UPF, right? That is least Riemann sum and upper Riemann sum. So in the previous session we have derived the formula for LPF, that is nothing but summation mi delta xi. Here I have already derived the value of mi, so I will just substitute that value here, and we know the value of delta xi, substitute that value also here. So you will be getting summation I minus 1 into c by n into c by n. This is nothing but c square by n square into summation I minus 1. You can observe here your summation is for I. So I have just taken c square and n square outside, and I have written summation for your ith term. So here it is I minus 1. So summation will be for I. Okay. So now LPF is equal to c square by n square into summation I minus 1. Now we have to find out this value. So I can split this as c square by n square into summation I minus summation 1. Right? So in your basic classes, that is in your high school classes, you have already studied the series sum of summation 1, summation n square, summation n cube, summation n power 4, so on. Here I will not derive that part. I will just write down the values. If you have any doubts, you can check your high school mathematics textbook. Okay. And one more thing is, you should remember this formula throughout your real analysis. So summation 1 value is n, summation n value is n into n plus 1 by 2, and n square is n into n plus 1 into 2n plus 1 whole divided by 6. N cube value is n square into n plus 1 the whole square divided by 4. Similarly, you will get for n power 4, n power 5, like that. Okay. So we will be using this formula here and there in your real analysis. So now for summation I can write n into n plus 1 by 2. So here we don't have n, we have I. So we can write this in that form also, or you can write it n form only, provided you have to mention here I is equal to 1 to n. Okay, so this will be c square by n square into n plus 1 by 2 minus summation 1 value is n into n. So if you solve this, you will be getting c square into 1 plus 1 by n divided by 2 minus 1 by n. This is just, here I have taken n common. So I will rewrite that step if you want. C square by n square. Here I have taken n common. So n into n is n square. You will be getting 1 over n divided by 2. I can write this n as n square by n. So this will be c square n square by n square into 1 plus 1 by n divided by 2 minus 1 by n. N square gets cancelled. You will be getting c square into 1 plus 1 by n by 2 minus 1 by n. This is nothing but the value of LPF. L of P comma F, that is lower Riemann sum for the partition with respect to the function. Similarly, first let us complete the part of your lower Riemann sum integral. Okay, so now let's find out the integral value of this, that is integral 0 to c f of x is nothing but x into dx. So you will be getting, we can write this as limit n tends to infinity L of P comma F, right? In the previous session we have seen this. So now substitute the value of L of P comma F. So it is limit n tends to infinity. L of p comma f is nothing but c square into 1 plus 1 by n divided by 2 minus 1 over n. This is the value of your L of p comma f. So we can write this as c square into 1 by infinity is 0. So I can write in this way minus 1 by infinity. So you will be getting c square by 2. This is the value of your lower Riemann sum or lower Riemann integration value, right? So now let's find out the value of upper Riemann integration. We can denote that as u of p comma f. U of p comma f is equal to summation capital Mi into delta xi. Here I have already found the value of your capital Mi, that is Ic by n. Substitute this value along with your delta xi value here, okay. So it is summation Ic by n into c by n. If you solve this, you will be getting summation I into c square by n square. I can write this as c square by n square into summation I. So again we know the value of summation I from the standard formula. I can write that as u of p comma f is equal to c square by n square into n into n plus 1 by 2, right? So this is c square by n square into, I will take n common, so it will be n square into 1 plus 1 by n divided by 2. N square gets cancelled. You will be getting c square by 2 into 1 plus 1 by n. This is my u of p comma f, that is upper sum of the partition with respect to the function. So now if I want to find out upper Riemann integral, I can write that as integral over 0 to c upper bound f of x dx. Here f of x value is x. This is equal to limit n tends to infinity u of p comma f. We know the value of u of p comma f. Substitute that and simplify. Limit n tends to infinity c square by 2 into 1 plus 1 by n. So I can write this as c square by 2 into limit n tends to infinity 1 plus 1 by n. Again if you substitute the limit here, you will be getting this part as 0. So you will be getting c square by 2, which is nothing but your upper Riemann integral sum. I will call this as equation number 1 and this as equation number 2. So from equation 1 and 2 we can write 0 lower bound to c f of x dx is equal to 0 to c upper bound f of x dx, and this is equal to integral over 0 to c f of x dx. Since these two are equal, it will be equal to your actual integration, that is nothing but your Riemann integration. So we can write that f of x is equal to x belongs to Riemann sum of closed interval 0 comma c. That means we have proved that the given function is a Riemann function, that is Riemann integral function, right? This is how we solve problems using Riemann integration method. Let's prove one more function as a Riemann integrable function. So this is the function they have given within this interval. Okay, what is our first step? I have to divide my intervals into n number of subintervals. For that we are defining the partition. Before that I have to find out the value of h. H is nothing but b minus a. What is the value of b here? It is 2 and a value is 1. So you will be getting 1 as your h value. So now define the partition. P is equal to, here a value is 1, so 1 comma 1 plus h is 1, 1 by n, 1 plus 2 into 1 by n, so on up to 1 plus I minus 1 into 1 by n, 1 plus I by n, so on up to 1 plus n into 1 by n, which is nothing but 2, right? So this is how I can divide my intervals. So now first what we supposed to do, we have to find out the value of your infimum and supremum for the interval xi minus 1 comma xi, right? So now what is xi in this interval? Xi is nothing but 1 plus I by n. Similarly xi minus 1 is 1 plus I minus 1 by n. This is the value of xi minus 1 and xi from the defined partition, right? So now we can write mi as f of xi. So here you have to be very careful because the function is 3x plus 1. So f of 1 plus I by n will be equal to 3 into 1 plus I by n plus 1, because the function is 3x plus 1. Wherever you have x, it will become xi. Okay, so 3 into xi plus 1, the value of xi is 1 plus I by n plus 1. So if you solve this, you will be getting mi as 3 plus 3i by n plus 1, that is nothing but 4 plus 3i by n. Similarly, let us find out small mi, which is nothing but your infimum, that is f of xi minus 1. It will be f of 1 plus I minus 1 by n. Substitute here, so you will be getting 3 into 1 plus I minus 1 by n plus 1. If you solve this, you will be getting 4 plus 3 into I minus 1 by n. So now we know the value of mi and capital Mi. Now I have to find out delta xi value. I can define delta xi as xi minus xi minus 1. So xi is 1 plus I by n. Xi minus 1 is 1 plus I minus 1 by n. If you solve this, you will be getting 1 plus I by n minus 1. Minus into plus, it is minus I by n and plus 1 by n. So I by n gets cancelled. Minus 1 plus 1 gets cancelled. You will be getting 1 by n as delta xi value. So now I know the value of delta xi, capital Mi, small mi. Using this, we can find out the value of L of p comma f and u of p comma f, right? So what is the formula for L of p comma f? It is summation mi into delta xi. Substitute the value of mi, small mi is nothing but 4 plus 3 into I minus 1 divided by n. This is the value of mi, and delta xi is nothing but 1 over n. Now I have to simplify this. So in order to simplify this, first I will just separate each and every part. We can write this as 4 by n plus 3 into I minus 1 by n square. I am just multiplying 1 by n to both the terms. Okay. So you will be getting 4 by n plus 3 into I minus 1 by n square. I can rewrite this as 4 by n summation 1 plus 3 by n square into summation I minus 1. We can write in this way, or I can write this as 4 by n. We know that summation 1 value is n, plus 3 by n square into summation I minus summation 1. So this is nothing but 4 plus 3 by n square into summation I is nothing but n into n plus 1 by 2 minus n. So we can write this as 4 plus 3 by n square. Here, as we did in the previous problem, I will take n as common. So you will be getting n square into 1 plus 1 by n by 2, and we can write this as n square by n. So you will be getting 4 plus 3 into 1 plus 1 by n by 2 minus 1 by n. This is your L of p comma f value. Now I can find out the integral value, right? So integral lower limit a to b f of x dx is equal to integral over 1, this is lower integral, 1 to 2 3x plus 1 into dx. This is nothing but limit n tends to infinity L of p comma f. Substitute the value here, simplify it, you will be getting limit n tends to infinity 4 plus 3 into 1 plus 1 by n by 2 minus 1 by n. So after solving this, you will get the value as, this is 4 plus 3 by 2 plus limit n tends to infinity 3 by n by 2 minus 1 by 3 by n, right? This part will become 0, so you will be getting 4 plus 3 by 2, that is nothing but 11 by 2. This is your lower Riemann integral value. If I get the same value for upper Riemann integral, then I can say that my function is a Riemann integrable function, right? So now let's check for u of p comma f. U of p comma f will be summation capital M into delta xi. We know the value of capital Mi, that is 4 plus 3i by n. Substitute this value along with the value of your delta xi. So that is summation 4 plus 3i by n into 1 by n. I can solve this as summation 4 by n plus 3i by n square. We can write this as 4 by n into summation 1 plus 3 by n square into summation I. This is 4n by n plus 3 by n square into n into n plus 1 by 2. So you will be getting 4 plus 3 by n square into 1 plus 1 by n by 2. N square gets cancelled. This is 4 plus 3 by 2 into 1 plus 1 by n. This is your u of p comma f value. So now integral over a to upper integral f of x dx is equal to integral 1 to 2 upper bound 3x plus 1 into dx is equal to limit n tends to infinity u of p comma f. Substitute the value over here, and using the limiting operation solve this term. Okay, so you will be getting limit n tends to infinity 4 plus 3 by 2 into 1 plus 1 by n. So it is 4 plus 3 by 2 into limit n tends to infinity 1 plus 1 by n. 1 by infinity is 0, 1 plus 0 is 1, 1 into 3 by 2 is 3 by 2. So 4 plus 3 by 2 is again it is 11 by 2. That means your upper Riemann integral and lower integrals are equal. So you can write that as this is equal to the actual integral over a to b f of x dx. Therefore, your function is Riemann integral over the interval 1, 2. Using the similar method, try to solve this problem in your assignment. This is your first assignment. You have to solve this problem in your assignment book. Okay. So till these 3 problems, in the function you are having x, right? So it was very easy to solve. Now let's see the example which consists of second order. Okay. So that is function f of x is equal to minus x square, which belongs to Riemann sum of interval 0, c. So here you can observe the function is little complicated. Now let's see whether this function is Riemann integrable function or not. First step is I have to find out the value of h. H is nothing but b minus a. In this the value of b is c and value of a is 0. So h value will be c. Now divide the partition. So p is equal to 0, 0 plus 1 into c by n, 0 plus 2 into c by n, so on. You will be getting 0 plus I minus 1 into c by n, 0 plus I c by n, so on up to 0 plus n by n into c. This is nothing but b. This is your partition now, right? So now I have to find out the value of xi minus 1. In this xi minus 1 value is I minus 1 into c by n. Xi value is ic by n. Now let's find out the value of delta xi. Delta xi is nothing but xi minus xi minus 1. So it is ic by n minus of I minus 1 into c by n. You will be getting c by n, right? So now I have to find out mi, that is lower sum with respect to the function f of x within the interval xi minus 1 xi. So this will be f of xi minus 1. Here you should be very careful because the value of f of x is not x or 2 minus 3x or something like that. It is minus x square. So f of xi minus 1 will be equal to f of I minus 1 into c by n. This is equal to minus of I minus 1 into c by n the whole square. Don't consider this minus and write it as minus x the whole square, because you can observe in the function they have clearly mentioned that the squaring is not for minus, it is only for x. It is minus x square, it is not minus x the whole square. Okay, so be careful with the function and substitute the value correctly. So you will be getting minus of I minus 1 into c by n the whole square. This is equal to minus into, I can write this as I minus 1 the whole square c square by n square. So now find out the value of L of p comma f. This is equal to summation I is equal to 1 to n mi delta xi. So summation I is equal to 1 to n. Substitute the value of mi here, minus of I minus 1 the whole square c square by n square into delta xi value is c by n. So you will be getting minus c cube by n cube, right, into summation I minus 1 the whole square. So this is in the form of a minus b whole square. Expand the formula, then apply summation to each of the term. So you will be getting minus c cube by n cube into summation I square plus summation 1 minus 2 into summation I. So now we know the standard formula for each of this summation, substitute here and simplify. So it will be minus c cube by n cube. Summation I square value is, in the beginning class I have written, right? It is n into n plus 1 into 2n plus 1 by 6. Substitute here n into n plus 1 into 2n plus 1 divided by 6. Summation 1 value is n. So it is plus n minus 2 into n into n plus 1 by 2. So now you have to simplify this. This 2 and 2 gets cancelled. You will be getting minus c cube by n cube into, here I can take n common from this and from this. So it will be n square. N square into n is n cube. This is 1 plus 1 by n into 2 plus 1 by n whole divided by 6 plus n. This is minus n into n is minus n square, minus n into 1 is minus n. So n gets cancelled. You will be getting minus c cube by n cube into n cube into 1 plus 1 by n, 2 plus 1 by n divided by 6. I can write this n square as minus n cube by n, right? So now I can take out n cube common. It will be minus c cube into 1 plus 1 by n into 2 plus 1 by n divided by 6 minus 1 by n, or we can write this as c cube by n minus c cube into 1 plus 1 by n into 2 plus 1 by n divided by 6. This is the value of your L of p comma f. So now you have to apply the limit here in order to find the lower sum, lower Riemann integration, right? So this is integral a to b f of x dx, which is equal to 0 to c minus x square dx, which is equal to limit n tends to infinity L of p comma f. So this is nothing but limit n tends to infinity. Substitute the value here. It is c cube by n minus c cube by 6 into 1 plus 1 by n into 2 plus 1 by n. Substitute the limiting value and simplify. You will be getting the value as minus 1 by 3 into c cube. Check this, you will get, okay. So similarly I have to find out the value of u of p comma f. For that I need the value of mi. Mi is nothing but f of xi. It is nothing but f of ic by n. Since the function is minus x square, it will be minus ic by n the whole square, which is nothing but minus I square c square by n square. Okay, so now u of p comma f is equal to summation mi delta xi. So it will be summation minus I square c square by n square into c by n. So it will be c cube by n cube into minus c cube by n cube into summation I square. So again substitute the value of summation I square. It will be minus c cube by n cube into n into n plus 1 into 2n plus 1 by 6. So you can take the things common here, that is n cube. You will be getting 1 plus 1 by n into 2 plus 1 by n divided by 6. N cube gets cancelled. You will be getting minus c cube by 6 into 1 plus 1 by n into 2 plus 1 by n. Now you have to find out the upper Riemann integration, right? So this is a to b f of x dx, which is equal to 0 to c minus x square dx, which is limit n tends to infinity u of p comma f. substitute the value of u of p comma f and apply the limiting values. So here also you will be getting the value as minus c cube by 3. Okay, so from L of p comma f and u of p comma f, you will be getting the same value. So you can write that integral over a to b f of x dx for lower sum and for upper sum is equal. So this is equal to integral over a to b f of x dx. Therefore, the function belongs to the Riemann integral over the closed interval 0 comma c. Therefore, the function is a Riemann integrable function. Okay, this is how we solve problems using Riemann integration. In the next session, let us solve some more problems and we will move to the next topic. Okay, thank you.